Thank you very much. My name is Lenka Pribylova, and I'm from Czech Republic, Masaryk University, and I'm very glad that I'm here in Lefkada. It's a very nice place, and I would like to talk about exploring synchronization mechanisms using bifurcation analysis. How to go on? The next slide, page down, probably. Okay, yeah, mouse. Okay, so probably you are not all experts in bifurcation analysis and in nonlinear dynamics. So I will start just to explain possible applications of bifurcation analysis. And I will start with well-known parts, and this is exploring mechanisms of branching. So you may imagine some dynamical systems that evolve, and we are seeking for birth of new types of dynamics. So this is one possible application. Another are mechanisms of abrupt changes. This is a case that has usually some switches from one type of dynamics to another. So this is also usually used in literature. And what I do with my team is exploring mechanisms of synchronizations. And so we try to explain various oscillational lockings. In fact, physicists usually use some kind of simulations on grids and using some ordering parameters and things like that. We don't do it. We use continuation programs for bifurcation manifold continuations. Specifically, it is MatCont, but you can use any. And so we are based on bifurcation theory. We deal with dynamical systems with parameters, and specifically we use ordinary differential equations, set of ordinary equations with parameters, and moreover autonomous systems. So the time is not explicitly written; it's only implicitly inside in the function x. So it looks like this is some kind of problem, but a lot of models looks like that, and we can also embed some other systems into this form, so it's okay. And what is most important is that the bifurcation theory and the methodology and the results also implemented algorithms into the continuation programs, that is everything proper and derived, and everything is already ready for the applications. So that's why we use this. And of course, it sometimes touches, for example, when you have a continuous system and you make some concurrent section. So at the moment, you come to iterative processes and other types of bifurcations of maps. So we sometimes use this. To start with mechanisms of branching, you probably can imagine that is related to some local or global bifurcations, that is qualitative changes of dynamics, and it is in fact case when there is some attractor in the system, and the attractor depends on the parameter, and you can draw some branch of this attractor with respect to the parameter. And there is also another branch. These branches may cross at some bifurcation value, and typically at that moment the branches change their stabilities. So this is the change and branching to another one. So this is one possible mechanism, and the most important feature of such systems is existence of the intersection. So usually, and I will show some examples of branches of equilibria because it's the most easy case, but of course it can be a branch of cycles, a branch of some invariant set, other chaotic attractor, something like that. When you seek for abrupt changes of dynamics, it is also related to some local global bifurcations, and it is usually related to some fault of the branch, where the branch of the attractor simply disappears, and the system has, when you cross the threshold value, the system has another attractor to go in. So the dynamics abruptly tends to another structure, to another type. And the most important feature of such a system is multistability, or at least bistability, and of course the folding of the branch. Maybe I will say some possibilities with applications. When you have bistability, so you, for example, you can have equilibrium and equilibrium, and you may make an abrupt change when you move from one basin of attraction of one equilibrium to another one. So this is example from our paper, one of my students and me, and it's a typical example when we explained that the predator has some inner alley effect, because when you go below the shaded region, so you lose the basin of attraction of the inner equilibrium, the predator extinct. This is very easy example. This is another example of bistability and possible changes of basins of attraction. And this is case of model of Josephson junction. It's a junction, superconductive junction that is used for either measurements or superconduction. It is the work of my former PhD student, now colleague Veronika Etzlerová, and colleague from South Africa, André Botta, who is a physicist. And you can see a red trajectory and a blue trajectory there. The red one tends to a cycle. This is a cycle that is its average voltage is 0, so it's the superconductive cycle. But the second one that is very close, I hope that you are seeing the winding, that it's living on a torus. There is an invariant torus in the space. In fact, the space is bigger. I made some projection into 3 dimensions because to see it, to visualize. And I think that you can see the cycle, that the trajectory tends to a cycle on the torus. It needn't be. It can be, but in the case that we tend to a cycle on a torus, in fact, this is, from our point of view, the thing that makes the cycles, the 2 cycles in the 2 directions to synchronize. So when you have this, you have synchronization. What is nice here, nicely visible, is that the basins of attraction are very close, because in this case, in fact, it's much more advanced theory, but there are heteroclinic and homoclinic connections of these attractors, and at the moment, the basin of attraction is fractal. So when you start very close with the trajectories, you never know where you end. Well, there are many other routes to abrupt changes: short-term parameter change that cross the bifurcation value. Also, there are other possibilities as saddle proximity, or when there was some attractor for close bifurcation value, and it's somehow ghostly present in the direction of the vector field, so it makes some ghost attractor there that makes the system to behave intermittent, for example. So the topic is very big, but I will talk really about very easy examples and about applications. I have 3 applications we did for the synchronizations. So about folding. Here we have a continuous and discrete dynamical system, of course with parameters. And when we seek, for example, for equilibria, we are not doing simulations. We are not computing trajectories. We compute solutions of nonlinear equations in this or that form. So this is the main advantage of our approach, because when we are computing anything, we don't use numerical methods for differential equations. We use Newton method only. And for sparse matrices, some advanced other techniques may be used, and the computations may be even faster for sparse matrices, of course. So when you imagine these let's say the left one, the equation that is related to the equilibrium of the continuous system. So the equilibrium is, according to implicit function theorem, is a function of the parameter if the Jacobian matrix is regular. If not, we have the fault probably. Of course, there are some other conditions, but here we will go to a very easy example, and I show it usually to my students because it's one-dimensional in the state space, and it has one parameter, and it is quite nice. You can see what is happening. It's a biochemical switch. X is a normalized variable that is related to concentration of the protein that is produced in the cell. And the first term here, the nonlinear term, is due to autocatalytic reaction. It's so-called Hill function, but doesn't matter. This function means that the protein is produced. And this is degradation of the protein. So this is very easy. The difference is the change and the derivative of the concentration of the protein. And you can quite nicely see that solving the equation on the right-hand side is very easy. You can see one branch that is 0, because you can take x out of the bracket, and then you have a function, not x of a, but a equal to x over 1 plus x squared. And when you look at the graph, exactly the fault of the second branch is at the point of the 0 derivative of this right-hand side with respect to x. So this is the Jacobian that has determinant or value at this moment equal to 0. Well, when you look at the application, it's very easy. When the concentration is high and you are on this upper branch, and A is in fact some ratio of the rates of the chemical reactions. So when A is low, so still the production of the protein is ongoing. And when you cross the threshold value 1/2, you simply cross the threshold and the production stops immediately, abruptly. So that's why the folding of the equilibrium manifolds are very important for applications, because you jump from one stable branch to another one, and you can explain what is happening. Okay, so I showed you an analytical approach. It's not useful much, because usually you even cannot compute a solution of, for example, you have a polynomial of 5 degree, and what you will do? Nothing. You have no possibilities to compute the zeros of the polynomial. Okay, but in case of polynomials, we have a paper about using a Grobner basis. I don't know, it's part of algebraic topology that computes some basis of a vanishing set of polynomials. So we can use this to avoid computing equilibria and to get the bifurcation manifolds immediately. Of course, using Maple, for example, or other softwares. And the main usage is through some continuation softwares. Numerical approaches are known. It uses some predictor corrector method, a Newton method. Simply you start on some known attractor equilibrium at this point, and you just move a bit and correct it to the correct place, and then you compute the branch, and you can see what is happening with respect to the parameter. Okay, so this is a case of equilibria, but in case of cycles, this is different. Usually you have no chance with analytic approach. I know one example when I can compute it. Of course, I do it for my students at lectures, but that's all. And we use, of course, numerical approaches. And the continuation is similar. You use some orthogonal collocation methods, or maybe shooting method or something like that, and you can compute also the branch, and you can detect the fold, because it's very easy. You can compute the multiplier of the cycle, and at the moment it crosses 1, simply you have the fold. So in case of equilibrium, it was a 0 determinant, and in case of cycle, it is multiplier, another multiplier equal to 1, because 1 at the cycle is always 1. So we have methods, numerical methods. That's enough. Moreover, because when we are seeking fold of the branches of the cycles, it's not easy to draw it, because when you have a cycle in 3 dimensions, for example, and you add another dimension as a parameter, you are in 4 dimensions. So it's not quite easy. But we also found some possibilities how to visualize this. And what is most important, there are 2 parametric bifurcations that guarantee existence of these folds of cycles nearby. So we usually seek for so-called Neymark-Zucker bifurcation, find the resonances, and nearby we find the branches of the limit point of cycles. So this is the method, but it's too technical, I think. So let's go back to the applications. I think that you all know the phenomenon of hysteresis. You saw it in applications. This is, in fact, the 2-parametric bifurcation that is related to this phenomenon. It's a normal form for this bifurcation. It's called cusp bifurcation. And you can imagine as you take a sheet of paper and you overlay it, or twice fold, or maybe a cover or something from cloth. So at the moment, when you look from the above to this manifold, so you see the projection of the folds as the V shape here. I think that you probably mouse. I think that you probably see this V-shaped region, and in this V-shaped region, we have bistability, because the folded plane or manifold has 2 parts, and in the middle usually there is some unstable one, and the 2 parts, upper and lower one, are usually stable. So we have 2 attractors. And when you go away from this V-shaped region, this so-called cusp, you simply jump from down to up, or from up to down. And this is the reason why hysteresis exists. In physics, there is a lot of examples. For example, in ferromagnetisms, of course, the hysteresis of ferromagnets, but also in combustion. For example, when you want to fire something, so you need much higher temperature, parameter is much higher, than when you want to put out the fire. So when you have to cool it down much lower. So the faults are in different places. I really love this example. This is from a well-known paper who started these applications. It's called catastrophe theory. Because it's about the abrupt changes that may change the system abruptly into absolutely different dynamics. And you see the parameters are pressure and temperature, and the manifold is density of the matter. So you can see this is liquid, this is gas, and these are changes of the state of the matter. And when you have very high temperature and very high pressure, you have some critical point here. This is the cusp point, two parametric bifurcation, doesn't matter. And above it, simply you cannot distinguish between gas and liquid. It's plasma, probably. Okay, but there are, of course, many other examples, biochemical switches. In population biology, it may explain complexity of ecosystems. Climatology. I think that you heard now a lot about tipping points. Tipping point in climatology is exactly fold of the manifold in our language of bifurcation theory. And this is a paper from Nature 2021. And you can see quite nicely this fold. This is the hysteresis, I think. I hope it's not visible here on the left side, but it is probably. And the horizontal axis is the global warming, so the degrees above the average temperature on Earth before the industrial age, something like that. And the vertical is flow strength of the Atlantic Ocean, of the main current that is interchanging the temperature in Earth. And you can see that when you are on the upper branch, it folds around 4 degrees above. And then the other branch is lower. So probably now we are touching the tipping point, and the Atlantic Ocean is slowing down, and the new attractor will be a low change, low flow. Well, other applications, epidemiology, social sciences, and many others. Well, so let's go to the synchronizations. I hope I have enough time. So I will show you just what we do with cycles. Well, this is a neuron model. Don't read it. I don't want you to. It's simply a membrane potential that is changing with respect to your ions that are going inside, outside through various channels. And the most easy model here has the first equation with the easy and most easy way how to write it this way, and with another state variable that is W, and this is some probability that the channels of potassium, okay, probably, yes, are opened. Yeah, so is the probability between 0 and 1, and it is opening the channels, in fact. These are parameters, physiological parameters. I have to say that we are collaborating on an interdisciplinary project with team in Hospital of Sun End in Brno. There is a department of neurology, and the reason why we are doing it is that they are measuring EEG signals of patients with focal epilepsy, and they found out that nearby the focus of the epileptic spot, that they measure much higher frequencies than they are possible to model and to physiologically fire by neurons. Absurd frequencies, over 2000 hertz. So we try to explain what is possible mechanism, because we don't know, of course, but we want to simulate this and try to help them to explain what is happening. Okay, let's see how the so-called bifurcation diagram looks for this neuron. This is external current in microamperes over centimeter squared, something like that, doesn't matter. And you can see this is the stable branch of the equilibrium, and this is the resting state of the neuron. The neuron's doing nothing, simply is living. But when you cross this threshold value, this part till this, again, another threshold value is called limit point of cycle value. So this is the folded manifold of the cycles. So in this area between 40 and around 140, there exists tonic spiking. That means that the dynamics is simply spiking in some natural frequency. And the question is, what happens when some other neuron is nearby spiking? So the most easy example is this. I made it only for this conference. So we use, of course, two neurons in physiological description. But here, I just easily drive it by some harmonic term to show that something is synchronizing. So let's see. At this moment, the system is not autonomous. We have to embed it into a higher dimensional system. We found out that the most easy way is to embed it into this system, where Y is in fact this harmonic term, because the third and fourth equations are so-called normal form of bifurcation that have solution that is stable for positive epsilon and has solution square root of epsilon times sine or cosine omega 2p 2 pi omega t. So exactly that solution. Moreover, here we can move the parameter epsilon, the amplitude, and the frequency omega. So the problem is that we have four-dimensional space. Easy thing is to imagine what is happening. Let's say the first two equations are spiking neuron, so we go in a circle. And the second two equations are not connected, and we have some driving frequency. So we have 2 dimensions, one circle, 2 dimensions, another circle. Cycle, not circle. Circle in the second case. And when we connect it, when we make a connection, so at the moment, the coupled system makes some movement on a torus. So you can see here the projection into 3 dimensions. Again, this is, this direction is the neuron, and this direction is only the projection of the Y state variable. And when the neuron and the forcing is not synchronized, you can see the trajectories on this invariant set that are so-called quasiperiodic. They don't tend to a limit cycle on the torus. In case it synchronizes, it simply has to move through some point, some border, into synchronization region where the stable cycle exists. So at this moment, we have a branch of a cycle, and in fact, topology says that when on a torus is a cycle that is stable, there has to be also a cycle that is unstable. So usually what we see is some kind of loop that when we continue the cycle, we see a stable cycle, fold, and an unstable cycle. So we can see what is happening. Also, we may study various lockings, because this is, for example, 1 times around of the neuron in the scale of neuron, and in the driving frequency, it's triple. So 1/3 sync. Okay, this is synchronization of the neuron. This is how the frequency of the tonic spiking looks like when it's driven by this forcing. Okay, I will show you the region of synchronization. That is the most important thing, because we can start from one cycle. We can find it somewhere, a stable cycle, stable synchronization. Then we can compute the stable, continue the stable cycle on this, for example, on this section. And we finish at the fold. And at the moment, you can see it also on this figure. You go back, but the pink curve, I don't know if it's pink or also there, probably violet or something like that. So it's unstable cycle that is living there. You may check, for example, the multipliers and etc. And you may check also other bifurcations. So here, for example, we found branch of period doubling, so the another mode 2/1. And this is the region of the synchronization. we don't need any grid computation, any initial conditions. We just start with one solution, continue, found the limit point of the cycle manifold, and then we continue this curve, and we know everything with respect to this parameter. Okay, what we did with two coupled neurons of this physiological model. This is now in submission process, this figure. We found out that for very low coupling, there exists another tank of synchronization. So we found not only synchronization that is in phase, that the two neurons that are together, close together and coupled, that they are firing the same way, but we found there is another solution, another branch of solutions, cycles that are in antiphase. So when one is up, the other is down, like that going. And you can see quite nicely that the branch, this is also Bistability, so the upper branch is in phase and the lower branch, the blue one of the cycles, is antiphase. And this is with respect to frequency, so you may quite nicely see what frequencies are there. And this is a case where we show that the neurons, I go back to this, and the figure is in yellow and red because the yellow one is the natural frequency of the neuron. So when they are firing synchronously, they simply are measured by the microelectrode as this frequency. But when you have two neurons and they are firing opposite, you simply get the voltage or potential that has doubled frequency. So this is the red one, red part. And we also tried it for networks, and it works, and it's quite in the beginning, of course, but we hope that we can explain much higher frequencies that are natural for neurons. So this is one example. Another, I already shown the Josephson junction that is also driven by alternate current. And you can see that here also inside there are signs, and we embedded it into five-dimensional system. So this is the embedding. And what we found out is exactly this bistability of the average zero voltage and the multiplying frequency synchronization. This is called in physics so-called Shapiro steps. I don't know if you heard about it, but usually they make this figure on the right. They simply have a grid, and they compute from some initial conditions and find out what frequency is there. And sometimes you can see that there are mistakes, because when you are already computing from some point of this top value, you may jump to another attractor, and at the moment you cannot go back. So usually there are some mistakes due to bistability, but we don't have it. We computed the same figure, also in a different scale, because big A is A squared is no, big A squared is small a, doesn't matter, simply different scaling. And we found out this by the limit point of cycle continuation. This is period doubling, bifurcation, and these are exactly these doubling and how is quadrupling, 4 times higher frequencies. Okay, and this paper already is out in quite good journal. Okay, and the last example is synchronization with season in ecosystem. So this is a project with my postdoc, Diptertisen, who got Maria Skłodowska reaction postdoctoral fellowship under me. And we study various synchronizations between in systems with patches, and this is only one patch, but synchronized with season. So the first equation is related to the prey, the second one to the predator. And if you know predator-prey models, you know that this part is a logistic part with alley effect. So it's effect that has a threshold of reproduction of the prey, that below this threshold the prey simply cannot survive. So they extinct. And this is the so-called response function of the predator, so how they are feeding, etc. And we imagine that the alley effect is influenced by seasons. So it's not only some level beta, but it has also some fluctuation epsilon. And in this system, also this is the embedding, in this system we also found the limit point of cycles manifolds, and we were surprised that the cusp shape has 3 borders. Because usually you have 2 borders, and what is it? So we found out that we need to visualize it, and at this moment we cannot visualize it with respect to frequency. You have to somehow visualize the cycle. Okay, in the neuron it was frequency, but now the frequency is frequency of season, it's 1. That's all. So we found out that the easiest way is to draw average distance of the limit cycle, the stable cycle, from the inner equilibrium that is unstable. And at the moment, we saw quite nice figure of hysteresis. So this part is non-synchronized, but there is a stable invariant torus. On this part is cycle on the torus, and it goes doubled. And again doubled again by a root to chaos, and there is also a chaotic region, even hyperchaotic region. And what we found is that higher levels of alley effect make the system behave more irregularly, of course. So in the beginning it is synchronized with season, so and when the beta is going up, you get biannual cycles and multi-annual cycles. Okay, so I think I come to the end. We hope that we bring some novel approach how to deal with synchronizations, because I know few papers that use bifurcation analysis for synchronizations. We can explore synchronization across various domains. I mean applied sciences. And of course, the disadvantage is that you need some advanced bifurcation theory, but not too much. It is universal for autonomous system. If you can model by autonomous differential equations, it's okay. You can embed the harmonic terms, but in other systems it is quite a problem. There are also some programs already for delay differential equations, so DDE2, for example. I heard, but never tried, also something for partial differential equations, so I can try to find it. And for large systems, there are already implemented algorithms by team of Yuri Kuznetsov, probably you know, he's author of Elements of Applied Bifurcation Theory monography, and he has around himself a huge number of colleagues from Netherlands and Belgium. So they made a new program for sparse matrices. So it can be used, for example, for networks that are small world network or ring networks or something like that. And of course, the methods struggle with when you have big system with a lot of parameters, you simply have to choose because when the matrices go bigger, the computation is slower. Sometimes it cannot be computed, but if you do it as a simulation, you come to the same problem. And of course, when there are coexisting solutions, sometimes you lose the branch. So you have to carefully understand numerics inside, that you have to set the steps and things like that. So sometimes it's a challenge, but we quite succeeded even in programs that looks like how it's called, stuff systems. Is it like that? Stiff, not stuff, stiff systems. Sorry. So that's all from my from me, and here is some references. Thank you very much.